Okay, so we have a projectile here, something that's flying through the air, and we're going to do some calculus to it to analyze its motion. They tell us it starts out with a velocity of 98 meters per second, and the first thing they ask is what will be the change in its velocity in the first 3 seconds. Now, this is not the kind of question we could give you on a test because it uses some physics principles that you may not be familiar with if you haven't taken physics before. For this example, that'll be okay. We'll fill in those blanks as we get to them. But if some of the things I'm about to say don't sound familiar, that's kind of expected with this one. This is a bit of a stretch. But if you have taken some physics before, you'll probably get a kick out of this. It's interesting to see how well calculus and physics work together. So, we've seen before that if you have a position function describing where something is, you can take the derivative of that, s prime, and that will be your velocity function, how fast you're moving, and you can take the derivative of that, and that will be your acceleration function, how fast your velocity is changing. So each of these things is the rate of change of the thing above it. Acceleration is how fast velocity changes. Velocity is how fast position changes. So we can differentiate to go down this list. We can also integrate to work our way back up, and that's actually where we're going to begin. For any object that's just flying through the air on the Earth's surface, assuming it doesn't have wings or engines to hold it up and change its trajectory so it just flies like a rock, the acceleration on it is going to be minus 9 point. Now, I've been trained to say 9.81, but in this problem, when they solve it, they simply use 9.8, and it makes the numbers come out a lot nicer. So let's pretend that that number is simply minus 9.8. That's our acceleration, which means it's the second derivative of our position. If we integrate that, we find its antiderivative. The antiderivative will be minus 9.8t, time is our independent variable, plus a constant. And we know what that constant is because they told us the initial velocity was 98 meters per second. So it's easy enough to solve for that c and find that it's plus 98. So the velocity starts at 98, and then we lose 9.8 meters per second of velocity every time a second goes by. So that's our velocity. If we were to graph it, it would form a nice straight line. It would start at 98, and then it would decrease 9.8 per second until over here, precisely at 10 seconds, because they cooked their numbers, we'll reach a velocity of 0, meaning this object will go up fast, up slower, up very slow, and it will actually stop and hang in the air for an instant right at 10 seconds because it's run out of upward velocity. After that, if it keeps going, the velocity will go negative and the object will start falling back down. So this represents rising quickly, rising slowly, stopped, falling slowly, and then it'll fall faster and faster until it runs into something. So for the velocity in the first 3 seconds, well, we already know that the velocity at time 0 was 98 meters per second. We were handed that. The next thing we need is how fast is it going at 3 seconds? And thanks to this formula, we can simply take 3, plug it in here, and that will give us the 3-second velocity. Minus 9.8 times 3 plus 98. What is that? Negative 29.4 plus 98. Is that 68.6, if I'm not mistaken? 68.6 meters per second. I'm going to confirm that. It was a risky thing to do in my head. Yeah, 68.6. Okay, so it started at 98 meters per second. It ended up at 68.6 meters per second. So the change in its velocity is what you'd get when you subtracted these, and it actually comes out to minus 29.4. That number popped up while we were doing our calculations. And this says the velocity decreased by 29.4 meters per second over the first 3 seconds. Now, I'm going to be typing the other questions here because there are some follow-ups and they're on separate pages of the book, so I don't want want to keep throwing up new pages on you, so we'll just jump from one to the next. The next thing they ask is determine the velocity time function for the motion of this object and use this to find the displacement in the first 12 seconds and the distance. And I'm switching the order here, but the velocity time function is actually what we got already. We said that the velocity as a function of time was minus 9.8t plus 98. That is a velocity time function. So we got that in the natural course of finding our velocity change. That part was easy enough. Now, if we're going to get into displacement and distance, these are two physics terms that mean similar things, but not exactly the same thing. If you're measuring how far you've gone when an object moves, there are two ways that you can do it. And one is called distance and one is called displacement. And I'll start with a boring example that will leave you wondering what my point is, and then I'll do another example that I think will clear it right up. Distance measures how much ground have you covered during a trip. So if you start somewhere and you go 6 meters east, and then you go another 4 meters to the east, the distance would be 6 plus 4 equals 10 meters. Distance is how you measure ground covered when you don't really care what direction it's in. You just add up all the distances. Displacement, what's different about that is that the direction is very important, and we represent the directions for displacements by calling them either positive or negative values. Generally, like with our x and y coordinates, we say that to the right is positive, up is positive, down is negative, left is negative. So if we were doing displacement here, we'd say this is to the right, so it's a positive 6. And this 4 is also to the right, so it's a positive 4. And we'd come out with positive 10 meters, or we'd say 10 meters in the positive direction. So in some cases, distance and displacement come out exactly the same, and you can get away with interchanging these words and nothing really happens. But here's an example where they don't come out the same. Let's say you go 6 meters that way, and then you double back and go 4 meters in the other direction. What happens now? Well, with distance, nothing changes. Distance is only concerned with how much ground did you cover. And so if you're doing distances here, you'd say 6 plus 4, and you'd still get 10 meters. Distance does not care that these are in opposite directions. It just covers, like, if you were to travel this much distance, how tired would you be? You went 6 meters and then another 4 meters, you're 10 meters worth of tired. Displacement, though, cares about the directions, and that's going to make a difference here. With displacement, you would say, I had a positive 6 because that's to the right, and then added on to that, I have a negative 4 because that movement was to the left. The total is plus 2 meters, or 2 meters in the positive direction. So displacement says if you go 6 to the right and 4 to the left, overall your displacement has been 2 meters to the right. Displacement isn't about how much ground you've covered, it's about how far are you from your starting point. And so with displacement, opposite movements can cancel each other out. Just one more real fast example, and then you probably will be fine with this. If you went 8 meters east, and then you turned around and went 8 meters west, what would the distance be, and what would the displacement be? Do you see them? For distance, you'd go 8 plus 8, 16 meters. You don't even pay attention to the directions, you just gather up all the numbers. For displacement, you have positive 8 and then a negative 8, and you come up with 0 meters. So while distance is saying, good job, you covered 16 meters there, displacement is saying, well, that was a waste of time, wasn't it? Overall, you haven't gotten anywhere because your positive 8 and your negative 8 canceled each other out. These are both valid ways of measuring. If you're doing an exercise program, distance is probably more relevant to you. If you go out for a run and you go 8 miles this way and 8 miles back, you totally haven't wasted your time. You've run your feet off. But for displacement, if you're measuring how far have I gotten away from my start, then yes, this is a waste because your movements have canceled out. So now that we have that, they want to talk about displacement in the first 12 seconds for our flying object, and that means, well, we better get a position function here. If we're going to talk about how far something has moved, we need to know where it is, and that means an antiderivative. The position for our projectile is going to be the antiderivative of this, which will be minus 4.9t squared. That's the power of t went up by 1, and then I divided by the new power. And we get 98t plus a constant. And what do we do with that constant? Do we know anything about the initial position? It turns out, yeah, we do. They said this object was projected upward from the Earth's surface, so when the time started, when this thing was launched or thrown or whatever it was, its position was 0. It was sitting right on the ground. It was 0 meters above the ground. And that means this c actually has to be 0. I could write plus 0 here, but I'm just going to throw that out and let this be our position function. And they want to know how far this thing went in the first 12 seconds. You can see s of t is a parabola. It opens down, and our object's going to rise fast, rise slower. We saw that it would top out and then start falling back down, and eventually it'll go thud and hit the ground again. And you remember when we were looking at our velocity, or you can see it looking at the velocity here, this thing's going to stop at 10 seconds. Right there is 10 seconds into the flight, and they're asking about 12. So you can see there's going to be some direction changes we have to worry about here. If we're doing distance, we're going to have to add up some positive distance up to 10 seconds and then some negative distance to get from 10 to 12 and combine those. Let's see how that works out. If we're at 0 seconds, our position at 0 is 4.9 times 0 plus 98 times 0 is 0 meters. That was easy. If we're at 10 seconds, 10 squared is 100 times minus 49 is minus 490 plus 98 times 10 is 980. We're at 490 meters above the ground right here. This is 10, 490. And if we're at 12 seconds, we're going to get, calculator time, negative 4.9 times 12 squared is minus 705.6 plus, and then we have 98 times 12, 1,176, and 1176 minus 705.6 gives us a height of 470.4 meters. So this point is 12, 470.4. So the two ways that we have of measuring here, one is displacement, and that one's actually easy. If you're measuring displacement, you say, I started at 0 meters above the ground. 12 seconds later, I am 470.4 meters above the ground. Therefore, my displacement is 470.4 meters. The other way you could work that out is to say the displacement is positive 490 for the rising part, and then negative 19.6 for the little bit that this fell down. And that would add up to 470.4 for the displacement. Now, if we're doing distance, things are a bit different. If we're doing distance, we don't care about direction. All of our numbers are considered positive when we're doing a distance. So then we would say we went up 490 meters. And then we went down, this is 19.6 meters. And so our total distance covered is 509.6 meters. For distance, both of these were considered positives, and so they add up to a larger total. For displacement, we have a big positive here and then a small negative here, and our sum is only 470.